Okay, this question rigorously is for an alkene system, but what I'm going to record is going to be applicable for exam, like the final exam, putting things in perspective, parts of it, even for exam 3. So it's a good idea to get used to that anyways. So you're given an alkene, it has a methyl group which is pointing upwards, and then we have bromine. You know about bromine that it goes through an anti-addition, and what that means is that the Br will either add from the top face or the bottom face and give you the product. So if you think about mechanistically how it's going to go, you will have one where you have the two BRs, or the two bonds to BR rather, and then the incoming BR is going to come from the bottom and it's going to attack, ring will open. So you will end up with a product that'll look methyl on top, BR on top, one BR at the bottom. And there will be another one where you would have methyl on top, BR at the bottom, this one, and this BR is on top. So that would have meant that the BR came from this side for the attack to take place. On the other hand, if you go with a transition state where your bromine is pointing downwards, then your incoming BR is going to ring open from top, and again the same thing can happen, and so you would end up with methyl still on top, bromine on top, the other bromine pointing at the bottom, and there will be another one with bromine on the bottom side, and this bromine would be on top. So there are four possibilities, and if somebody asks you, well, what is the relationship between them? Well, realize that these two are exactly the same. This guy and this guy end up being the same. Likewise, the other two are exactly the same. So if you wanted to really compare and contrast, in terms of what's their relationship, you have to compare the absolute stereo chemistry, and so you can say this one will come out to be R, R, and R. So again, you're going to go with the priority order. Bromine is going to get the highest priority, followed by the carbon with the bromine bond, followed by the carbon with the methyl bond, and then the hydrogen. So you're going in 1 to 2 to 3, you're going in a clockwise direction, and that means that it will be an R. So I went ahead and assigned these are all R, 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 and I'm getting in the other one. So if this is R, this guy is going to be S, and this guy is going to be S as well. So if you have two combinations RRR with RSS, the relationship between them should be diastereomeric. You would have called it enantiomeric if it would not be RSS but SS. So every single chiral center would have been the inverted configuration. That's when you would call it enantiomeric. Since in this case one of the R's is retained, we are going to call it a diastereomer. Let's do another one in terms of the kind of reactions that we have done, so we know what we are talking about. So we've gone over SN1, SN2. Let's say, and this is similar to, the kind of question that that I discussed within the wikis. Let's say that's your starting material. You're treating that with HCl. Eventually, you're supposed to carry out a substitution reaction, and you're supposed to predict the products. Okay, so the box is drawn, and you're told that the alpha optical rotation of the starting material is, let's say, plus 60. And you're treating it with HCl. Turns out that alpha of what you get is 0. And now you have to predict what's going on, why would that be, what's happening. So first things first, if you're supposed to figure out, give information about the mechanism, you should show the protonation. Cl would leave. That will be OH2 with a positive charge. So that sets the stage for getting a good leaving group. And that gives you a secondary carbocation on which the Cl can attack either from top or from the bottom, one or the other, and give you, strip pH, give you, H and Cl, and the other product will be Cl and H. So these are your options. Since it's a carbocation, it's a racemic mixture. So half of the molecules are going to go through the attack from the top, the other half is going to go through the attack at the bottom. Since it's a 50-50, that is the reason that alpha is going to be 0. So the net product that you're getting is because this is a racemic mixture. Other reasons that you might see this would be if the chiral molecule loses its chirality, it becomes like a double bond or something, then also you would say that it's achiral and alpha would be 0. And the third reason, of course, is if your structure is a mesostructure. So those are your possibilities. But now that you have your product, you can say that alpha is 0 in this case because it's essentially a racemic mixture. The attack on top and bottom is equally likely, so half of the molecules are going to turn the plane polarized light in the forward direction, the other half are going to turn it in the backward direction. And that's about it. Okay, let's take a look at this problem. It just basically is a reaction summary thing, just to kind of get you to recap all the reactions that we talked about in class about alkynes. So the first one suggests that you have an alkyne and we are treating that with something and it's giving you a ketone. Notice my benzene ring is going to be intact and it's these two carbons 1 and 2 that you're going to see the reaction in. And right now it seems like the C double bond O is going to get formed specifically at the benzylic positions. That means you have to add water because you have an oxygen now, and the three ways that we talked about that you can include an oxygen is by getting it to add HOH across the point of unsaturation, and then we can think about, in case of an alkyne, we can think about the tautomerization to convert it into a ketone. So the first step should be the addition of water, and the way you can do that, since you're following in this case the Markovnikov's rule, and I know that I'm following Markovnikov's rule because the terminal carbon C2, which contains the hydrogen, it's getting converted to CH3. So this carbon is 1 and this carbon is 2. So my reaction condition for that is that in presence of acid and mercury, I'm going to add water. And that will give me first, let's perhaps use the green one. It will first give me the addition of water, HOH, across the triple bond, and then it's going to go through the tautomerization, the shift of that hydrogen, to give you the corresponding ketone. So recall, acid, water, and mercury on alkynes, add water according to the Markovnikov's rule, you end up with methyl ketones. That's what we learned. Now, on the other hand, if you wanted to add water to the terminal position, so if you wanted to get a different kind of enol, which looks like this, and is going to tautomerize into an aldehyde, in that case, you want to follow anti-Markovnikov rule, and you're going to go with BH3 THF, H2O2, sodium hydroxide. So peroxide, BH3 is the only method that you know for anti-Markovnikov rule, in addition to the HBr addition with H2O2. So keep that in mind. That's a handy reference. Presence of H2O2 is anti-Markovnikov rule. The third reaction is basically I have carbon 1 and 2 next to the benzene ring, and I have completely achieved saturation. So the best way to go about it would be to simply use hydrogen and palladium. Notice in this case you do not need a Lindlar's catalyst or liquid ammonia or lithium, things of that nature. Reason being, you don't want to stop at the alkene stage. You want to go all the way to the saturation level. Now, I have two cases here. Okay, so I have a triple bond going to a double bond, and I have two of these. Notice, in this case, really speaking, for this specific case, it doesn't matter what reaction condition you would put as long as you're going from the triple bond to the double bond. Reason being, because you have two hydrogens on this particular carbon, the cis and trans doesn't really make sense because the groups are exactly the same. So at any given point of time, this hydrogen is going to see one hydrogen, and hence cis and trans doesn't matter. But just because it's been drawn in a cis fashion, I would say that here you can put in hydrogen palladium with barium sulfate, which is a Lindlar's catalyst. You can also use hydrogen palladium and calcium carbonate. On the other hand, on this side, you would want to use something like lithium and liquid ammonia. So those are two different things. But that is only because of the way that these are drawn and nothing else. You can write it either or. On the other hand, if you had an alkyne, like an internal system in which you did have the option of getting a trans versus a cis, or a cis versus trans, you would then be you should be sure to follow the correct reaction condition. Okay, let's take a look at the next one. I have here two carbons that I'm beginning with, and notice I'm going 1, 2, 3, 4, and 5. Oh, sounds like I just added carbons. What must I do? What are we thinking? You should think about chain elongation. That means there should be some method of getting rid of this acidic proton on the alkyne, on the terminal alkyne, and you can do so by treating it with a strong base like NaNH2 and follow it with, notice I already have one carbon, two carbon. I have two carbons and I need 3, 4, and 5. So I need 3 carbons there. So how about I treat it with bromopropane? And so that should give you, first, let me write in green, a new alkyne, 1, 2, 3, and then 1, 2, 3. So we have added the third, fourth, and fifth. First and second carbons were already there. Now it's your job to convert your alkyne into a ketone. So you might wonder, Markovnikov, anti-Markovnikov. In this case, again, realize the substitution pattern is the same in both of those. Whether you use Markovnikov or anti-Markovnikov doesn't matter. But since we know that in case of the Markovnikov rule, we want to follow sort of the most stable carbocation, even though in this case it will be a vinylic secondary carbocation. That secondary carbocation also happens to be at a benzylic location. So I would use, in order to go from here to here, I would use acid, mercury, and followed by water. So acid, water, mercury, that concoction will give you the ketone. In the next one, I'm adding 2 bromine, so that's pretty straightforward. Just basically treat it with Br2 and CH2Cl2. The reason why you're using CH2Cl2 is because you want to keep essentially 2 bromine atoms rather than a bromine and water. If that is what you would end up with, then you are going to end up with a Br and an OH in the system. But in this case, since that you had to add 2 bromine, you go with Br2CH2Cl2. Anytime I'm asked a prepare question, I always think about what I have been given and where do I want to go? What do I have to form? And that helps me in analyzing the prepare as to where the functionality is. Notice in this case, both your OHs, they're on the solid line, which means that you have a cis-diol. So you should be thinking right now, what are my ways to get a cis-diol? Well, first things first, in order to get a cis-diol, you need a double bond. And then you know that if you treat that with osmium tetroxide, pyridine, followed by sodium bisulfite and water, that should give you the desired product. And so now your aim becomes, well, can I convert this given alkyne into this alkene? So I want you to get your attention to this double bond over here and see how many carbons you have. If you notice this triple bond over here, I have 1, 2, 3. So those could end up being the same chain that you have in the alkene, and that means you have to definitely for sure carry out a chain elongation. So if I were you, I would begin by treating this with NaNH2, follow it with a 3-carbon iodo-propane, bromopropane, whatever you want it to be. And then we'll add the 3 carbons. So I have my alkyne. Convert this alkyne into alkene, and in this case, you want both of those. So you can use, in Lindlar's catalyst type manner. And then treat that with osmium tetroxide to get your cis diol, and that is it. That's your prepare sequence. Let's take a look at another one. I have an alcohol, and it's giving me a dialdehyde. So, what are some of the ways that you know that you could get a dialdehyde? Well, whenever you have, and this is my advice to you for both organic 1 and 2, whenever you see like a diketone, dialdehyde, so 2 carbonyls within the same group, it's a good idea to think about it as if the snake was biting its tail and now is, in its open form, so it's wriggling around. So the snake was biting its tail and now it's not doing that anymore, so it's laying down. What that means is what would happen if you have 1, 2, 3, 4, 5, and 6. If you bring these 2 aldehydes and click them together, that means, in other words, if you had cyclohexene, you could carry out like a ozonolysis type reaction and get the 2 aldehydes. So now the question is there a way that could convert the alcohol into the alkene? And the answer to that is dehydration. So treat this alcohol with H2SO4 and heat. That will give you the alkene. Carry out ozonolysis followed by zinc and acetic acid, and that will give you your product. Done. I have said this before and I say that again. It's always a good idea to count your carbons. So let's say you have something like perhaps this alkyne, and you're treating it with NaNH2, and then you have a box, and maybe you're just hydrogenating it with palladium, barium sulfate. So that's going to stop at the alkene stage. It's a good idea to count the number of carbons. So 1, 2, 3, 4, 5, and 6 you have on their own. And this is the carbon that's going to lose that first proton. And then I have 2 more carbons that are going to come from the Br. So the first step is going to be the generation of the alkylide. So you have a 6-carbon chain. And 3, 4, and 5. And that is then going to add to your carbocation and substitute that bromine. And you will end up with triple bond still. So 1, 2, 3, 4, 5, and 6. And I'm supposed to be adding 2 carbons, 7 and 8. And then the next step is that I do a hydrogenation, but in presence of Lindlar's catalyst. That means it's going to stop at the alkene stage, and it'll add in a cis fashion. So you should draw the double bond and then put the 2 H's in the same direction. So draw it in a manner that is reflective of the cis, not the trans.